In this video, I will talk about Trojan messages in distributed systems. One of the main reasons for choosing a distributed architecture instead of relying on a single computer is fault tolerance. A distributed system should be able to handle the failure of several its components while still providing service to the clients. However, the components of the distributed system need to communicate with each other via messages they send over the network. Sometimes it may happen that the messages themselves can become bad. For example, when they are sent by a corrupt machine, the messages may themselves be corrupt. Such bad messages can be sent to correct components of the system and in turn corrupt the correct components of the system and even bring down an entire distributed deployment to its knees. In my work, together with Professors Candea and Rachid Guerraoui at EPFL, we want to help distributed system developers find such issues in their code. We define Trojan messages to be messages in a distributed system that are accepted as valid by receiver nodes. However, they cannot be sent by any correct sender node. So, if we have a receiver node that accepts as valid rectangles, triangles, diamonds and circles, but we have a sender node that can only send rectangles, triangles or diamonds, then the circle is a Trojan message according to our definition. We argue that Trojan messages are a source of vulnerabilities, because on the one hand, they can trigger corner case behavior in the system, which is often difficult to get right, while on the other hand, Trojan messages cannot be discovered with regular end-to-end testing, and therefore the developers are likely unaware of their effects. We proposed and implemented an approach to automatically discover Trojan messages in the implementation of a given distributed system. Our approach, which we call Achilles, uses dynamic analysis on both sender nodes and on receiver nodes in order to find all the messages that the sender nodes can ever generate and all the messages that receiver nodes can ever accept as valid. Essentially, we extract a representation of the grammar of messages in the protocol used by the system, and then we compute the difference between the two. Although the message grammar should normally be the same in both the client and the server, we find that there are often subtle differences between the way it's implemented, and thus it leads to Trojan messages. Achilles uses symbolic execution in order to extract the grammar of the sender and receiver nodes. Essentially, symbolic execution systematically enumerates all possible execution paths in the binary of the sender and of the receiver. The receiver does something like this. It first receives a message over the network, and then it switches in order to check the type of message. So, on one branch it will check if the message is equal to the square, in which case it accepts the message. On another path, it will check if the message is a triangle and also accept, and so on. The sender, on the other hand, receives an input from the user and then also parses the input in order to check what type of message to generate. Using symbolic execution, Achilles will explore all of these execution paths. So in the receiver, it will explore these execution paths, while in the sender, it will explore these execution paths. In the receiver, it will explore all execution paths that lead to the message being accepted as valid, while in the sender it explores all execution paths that lead to a message being sent. Finally, Achilles uses satisfiability modular theory solvers in order to compute the difference between the two grammars and find the set of Trojan messages. I have only given here a very high-level view of Achilles. There are actually several hurdles that we had to overcome in order to implement a working prototype of Achilles, and you can find a more thorough explanation in our paper at ASPLUS 2014. In the paper, we describe some real Trojan messages that we discovered using Achilles. The messages lead to some subtle bugs that would have been hard to discover using other techniques. For example, a Trojan message can lead to a denial of service vulnerability in PBFT, which is one of the most well-known Byzantine fault-tolerant state machine replication systems. Suppose you have a PBFT deployment consisting of 4 replicas, one of which is a primary. Client nodes of PBFT generate messages and authenticate them using 4 private key authentication fields, one for each replica. Suppose that we have a malicious or even a buggy client which generates a message that has correct authentication fields for the PBFT primary but has incorrect fields for every other replicas. If the client sends such a message to the primary will check its own authentication field and see that it's valid, and will then broadcast the message to every other replica. Now, the other replicas, when they check the message, they will detect incorrect authentication fields, and therefore they will see that the message is incorrect. However, the replicas have no way of knowing whether the client has corrupted the message, the network has corrupted the message, or the primary has corrupted the message. Therefore, the only safe action for the other replicas to do is to actually vote and change the primary, because it is suspected of being malicious or of being faulty. However, the primary change mechanism is an expensive operation, and therefore it slows down the entire system. And this is actually the essence of the denial of service attack. Now, the essence of this vulnerability is the fact that the primary does not check the authentication fields for the other replicas. It only checks the authentication field that was intended for itself. Therefore, it accepts a message that has incorrect authentication fields, namely authentication fields that no correct client could ever generate. This is, in fact, a Trojan message. In this case, the vulnerability is by design, because the authors chose private key authentication instead of the more costly public key authentication. However, the key thing to keep in mind here is that Trojan messages can have very subtle effects and that Achilles can find such bugs automatically.